Hi there. So we've taken a look at the ExplosiaFX domain in general, or the ExplosiaFX dynamics object in general. We've looked at the basics of the solver tab, the bounds, and the display tab. Now we can take a look at sort of more of the detail of this solving tab and also the simulation tab. If I just press play, we've got our default scene back. Let's put our motion back on our vibrate tag. And you can see I've got it at 6 voxel size, so it's quite quick. And we've got this nice fluid being solved in the viewport. Okay, so what we're going to look at now is we're actually going to look at this adaptive bounds and what this means. So it's quite important. You can see down here we've got this adaptive bounds. If I reduce down, if I make this a bit larger, actually let's pull this panel up. We can see here we've got this adaptive bounds. Now what does this mean? We've done something like this, we've dealt with something like this in the flip domain. Essentially what it's looking at is it's looking at keeping the simulation efficient. So if I have adaptive bounds completely off, I press play, the whole container fills up. It starts to solve every single voxel. And even though at this resolution it's not too much of a problem, as you get to higher resolutions, your memory footprint and your simulation speed would be significantly diminished if you're constantly solving, especially at the early stages, the whole domain. You might even run out of RAM if you're going incredibly high resolution. So I'm going to put adaptive back on, and you can see this box starts to follow the simulation quite tightly. And that's all this is doing. It's actually adapting, and then each time it adapts, this adapt size basically means how much of a buffer between the actual solved voxels do we give and start to track. So basically, if I increase this to like a crazy high number, you'll see it stepping much more significantly. Can you see there? That's 100 units around the simulated voxels. If the voxels are below a certain threshold, they will not be counted in the adaptive simulation. So you can see here, I'm going to drop that back to 4, and we're going to take a look at these other values here. And I can turn off tracking the smoke, I can turn off tracking the fuel, the color, all separately. So I can turn off tracking color because we're not even using that right now. We don't need to turn that off, it's just the way it is. We can turn off track heat, and we can turn off track smoke, and it'll only track the fuel and the velocity. And you can see here, it's actually clipping wherever the smoke gets to. But if we go to our display tab and display just the fuel, we'll see that the fuel is simulating fine. So if we're doing fire simulations here, we might want this to be just tracking the fuel. And that's really important if you're doing, a really long fire simulation. And this keeps the cache small, the simulation time small, and your producers happy. So if I click track smoke or track heat again, we'll get this, it'll start to move away and track the whole object or the whole simulation. Let's go back to our fuel and smoke simulation. There we go. Back to our solver tab. Now the thresholds at which the container adapts, basically that means that the smoke threshold it'll stop adapting the container if the smoke value is below 0.01, which is actually, if you think about it as a percentage, it's 1%. So if the smoke value is below 1 at the unit of 0.01, the container will not adapt. But if it is above that, it'll look at that voxel and it'll say, oh, this voxel contains more than 0.01 smoke, adapt. Otherwise, if we have a too high a value, so if I make these all really high, we don't need to worry about color. We get absolutely no adaptation at all. And in fact, you can see there's a tiny bit here where the smoke is just about simulating in the default adapted voxel. So if I drop it down to 1, you can see it kind of starts to go crazy because it's clipping and it's finding some parts of the fuel threshold is at 1. If I drop it to 0.5, oh, we're getting somewhere, but it's still clipping down as soon as the smoke gets to a certain value. You can see it's causing all sorts of problems, and this wouldn't be a very nice simulation. So the default is this 0.01. You could probably increase it, but what that means is the container, the adaptive container or adaptive bounds would stick very closely to your fluid, and what you might end up getting is the nice curling smoke squared off in places. And the adaptive container actually starts to dictate the shape of the fluid simulation, which you do not want it to do. You want it to just be just close enough that it doesn't use up too much memory, but far enough away that it doesn't affect your simulation. And you'll find there's certain levels of balance there. The heat threshold is a bit higher because heat rarely goes below a certain parameter, and also these other ones adapt as well. And like I said, you can turn off these channels. We've seen that already, and there we go. So that's the adaptive bounds. Or pretty much leave those on default in general. Your velocity threshold becomes more important when you're using fast-moving objects, fast-moving particles, for instance, and it also depends on the velocity value inside your source object. So, for instance, in particles, you actually have a velocity multiplier, and we'll deal with sources maybe in a separate video, or maybe at the end of this video. Okay, so that's adaptive bounds. That's how you keep your simulations nice and small and fast. Initial state. Now, if you're dealing with sort of look dev, or you're even just trying not to, you basically want a simulation to start later on down the timeline, or you want it to start with some fluid already simulated, we can set an initial state. This is really very useful. I'm going to press play up to quite late on. I might go to the right towards the end, maybe frame 80 or something like that. And what we're going to do is we're going to set an initial state. So I'm just going to press pause on 80, I reckon. Oh, good hit. What we need to do, just need to click, just like in the emitter, we set initial state, and it stores that state. Now, obviously that's quite a large thing there. So what that's done is it's stored that in memory, and your memory of your scene will actually increase when you save the scene with this initial state saved. So just be wary of that. Won't be too bad. This is quite a small frame at the moment. So I've set the initial state, go back to the beginning, press play, and immediately we start with what was the 80th frame of our simulation. And I press play, and it'll continue simulating because we've got our source tag. If I turned our torus off, it would still simulate. It would just carry on and dissipate the smoke. Okay, so that's set initial state, and we can save those and we can load them into other containers. Got to be a bit careful with that one because sometimes you get voxel differences and things like that. But the main use for that is just to begin with a certain amount of smoke. Probably the most useful scenario for that I found is when doing a scene with fog in it. You need to set an initial state for the fog. So instead of having to emit all the fog into the scene, wait for it to churn around a little bit, and then start rendering your scene, you don't have to do that. You can set the initial state, and then it's already in a churned up state at the beginning, and you can kind of go from there. It's much more efficient. So I'm going to clear that state because we don't want that to be saved in there. And let's have a look at our simulation tab. What do we have in here? So the simulation tab is actually where the magic happens, really. This is all to do with the physics of the simulation. This is how you can control buoyancy, gravity, which sounds weird. Gravity in a fluid sim doesn't look like it has any effect, but we'll talk about that in a minute. We have vorticity, pressure. Pressure is a huge thing in here, but it's not exposed too much to the user. I'll talk about that in general terms. Diffusion, which is how it kind of diffuses into the other voxels. Dissipation is how much it decays over time. And then burning models. Burning models are really cool. It's about how you turn fuel into smoke and that kind of thing. Okay, and we might talk about UVs later on, but that's quite an advanced topic. But mostly we're just going to take a look at the main parameters in here. So let's first take a look at sim scale. Now, sim scale is a way of having your container stay the same size, but then have it fit into a scene that you've scaled up or down. So for instance, if you work at scale, by the way, that's highly recommended that you work at scale, just purely because it helps all the other parameters. You know, render engines like to work at scale, dynamic systems like to work at scale. But in a voxel domain like this, scale is actually arbitrary. It's arbitrary in Cinema 4D itself. But what I mean by that, or abstract even, is that the container itself can be scaled regardless of the scene. So whatever the scene scale is. So it doesn't know that you're in a scene that's 1 meter by 1 meter and you've got a guy that's actually 50 foot tall. You need to, you might need to adapt it to that scene. So you have to actually tell it what the scale of the scene is. So say I drop a guy in here. Let's drop a photorealistic human model. Yes, trusty old figure. So this is he's actually at a real scale. So he's actually at 180 centimeters, which is 6 foot, or just under 6 foot. And so he's roughly real scale. Now if I press play at the default 100% scene scale, I've increased the resolution here, by the way, as well, just to, I might drop that back down to default. Let's play. And you can kind of see this, actually let's go back to high resolution when we actually get there. So this is the scale of the smoke. Now really, smoke at the scale that he's at would be, imagine a fire in front of you. You know, it's much more detailed. And I'd say this is about 10 times to the size of these vortices is huge. You know, you don't tend to get those in anything but perhaps maybe an extremely cold environment where there's not much turbulence in the air. So what we need to do, we need to actually reduce the size of the simulation. Now that sounds a bit counterintuitive. You think that we're going we're upscaling because we're not upscaling, we're going to a higher scale because currently this, if I just scale this down to like 10% of its size, we just reduce it and make it smaller. But actually what we're trying to do here is we're trying to balance out the look of the vorticing and stuff. So our source object remains the same, but you can see we're getting way more detail and much more kind of small vortices in our smoke simulation. And this is really important. I know it sounds a bit boring to talk about scene scale and stuff like that, but all the parameters get scaled with this percentage value. So what that means is we get a much more realistic smoke emission at scale. So if you're blowing up a tank, you're having a trail behind a plane, and your plane in your scene is 10 times smaller than it should be in real life, you need to be able to have a slider for the scale of your simulation. So that's all this is for. A little warning with this scales everything, including the adaptive container, which we just looked at, the adaptive bounds. I keep calling it a container. It is a container, but it's bounds as well. So if we go to the simulation tab and go higher, it's not a problem when you go lower, but when you go higher on the sim scale, which essentially is saying that we're basically saying, okay, our guy is gonna be 10 times bigger. Think about this. So he's much bigger. Say he's got a candle in his hand. Yeah, this is going to win some awards, this. We can increase the sim scale. And when I press play here, we can see that the simulation is smaller. We also see this problem that I wanted to show. And that's that we need to watch out for the adaptive bounds, which are also scaled with this sim scale parameter. So actually let's go for actually that sim scale's fine. Let's stick with that. 200%. It doesn't quite work like that with the adaptive size, so we need to look at two of the real world values here. So we need to look at the adaptive size and the velocity threshold. Currently it just clips. As soon as it sort of reaches the usual point where it would start adapting, it actually clips. So we need to do two things. We need to increase the velocity threshold because we've changed the scale. So I'm actually going to drop that right down to 10, and still not seeing much of adaptation. But then we need to also increase the amount that the adaptive size. So let's go to 30. Let's try that. And there we go. We're seeing it's adapting much better. You might want to play around with these other smoke threshold parameters, but they tend to remain the same even when the scene scale is being done. And you can see that's a pretty aggressive scene adaptation. I'd probably come back to 100 on the threshold here. But you'll find a balance. You need to, like I said, you need to keep it as tight as possible, but away from the smoke from changing its shape, I should say. Okay, so that's messing around with the scene scale, or the sim scale, I should say, not scene scale. That's a totally different thing. And it's useful to have when you drop it into, say, imagine you have like a battle scene on a huge battlefield. Getting quite ambitious here. But say you've got a huge battle scene, and there's smoke drifting across it. You know, if you use the default, it might be way too large, which makes it look soft, and it might the battlefield look like toy soldiers with the scale. So it's really worth looking out for scale. Just in any 3D workflow that goes for as well. You know, even if it's just modeling, rendering, everything, scene scale is very important. Okay, so then we have this next one. Of course, this is a pretty obvious one. Let me go back to our... I'm going to make it smaller so it plays a bit more in real time. There we go. So we're getting about 10 FPS. Okay, so this is the sim speed. This one is essentially a retiming value. So if I drop it down to 10%, we essentially get this sort of very slow simulation. It would rise, but we've just reduced it by 10. Let's go to 50%. And there you go. You can see it's much slower. By the end of the simulation at 100%, we're actually hitting up the top here, and we're only hitting there. We can speed it up. You can see here it aggressively goes to the top, and by the frame 25, we're already well beyond. So this is cool for like slow motion, retiming, that kind of stuff. Because if you simulate, there's no subframe steps in the same way that you have with particle positions, because it's hard to interpolate between them. So, or not that I know of at least. And so therefore, it's best to do retiming in the simulation for the ExplosiaFX stuff. Okay, that's a nice and easy one, sim scale. Now, buoyancy. What is buoyancy? And how does it apply to our fluid simulation inside ExplosiaFX? Well, buoyancy in the real world, probably the simplest description of it is where you've got different densities of objects in different density mediums, and they move around each other, or they move each other around in different ways. So, simplest example that we understand as humans is in water. Some things float and some things sink. And the reason they float or sink is if they have lighter, if they're denser, so if they're heavier, denser, more molecules packed into an object, they will sink in a fluid, like water. So you've got a stone, it'll sink in water. And then if you've got, say, an air-filled dinghy or a balloon or something, that is obviously lower density because the air is a lot less dense than water. That will float to the top. And that's the simple way to think about buoyancy in a fluid simulation as well. So smoke or fuel can be heavier more dense than the air around it, and therefore will want to sink. But then heat, when you think of it in terms of heat, buoyancy, you might have heard it called convection. So essentially, the hotter something is, the less dense it gets. So the molecules are excited. The less dense it gets, the more it will move up it'll have a buoyant upward force, and it'll actually carry the smoke with it. So often you'll see these swirls happening. Most of the time you see smoke rising in the air. It's not because it's less dense than air, it's because it's being carried by the heat. So that's just a basic explanation of buoyancy. There's plenty of documentation online, great videos on it, and all that kind of stuff. For our purposes, we need to know that buoyancy is going to make our fluid go up or down. That's it. So gravity is important in buoyancy because that's what's creating the pressure differential and pushing things down. Obviously, in our simulation, it's a downward force, center of the Earth and all that. But gravity, we can exaggerate things, but we don't want to. That's just a multiplier, if you like. Smoke buoyancy. So let's press play. Let's get our simulation going. So currently, our smoke buoyancy is at negative 20. This is like the default. Is it negative 20? Yeah, negative 20.1. Interestingly, and what we see it getting carried up the top there. Now, if I make it, with a negative buoyancy, it should be sinking, right? Well, that's being carried by the heat. So the temperature buoyancy is actually creating our velocity vectors that is overpowering. So actually the difference here is 80. So there's it's enough to overpower the smoke buoyancy. If I decrease the smoke buoyancy to 60, for instance, below 60, you can see now that it almost balances itself out, and the temperature's trying to get it to rise up, and we've got this vorticity occurring, but it's enough to kind of nullify the motion of the thing. And if I make the fuel negative, actually it's not very evident at the moment. I'll show you fuel when I've got a more distinct fuel channel in a second. But the defaults are negative 20 and the heat buoyancy at 60. If I make the heat buoyancy 0, so that the temperature is no longer carrying everything up, the smoke and the fuel will overpower the simulation and they will sink. So you can see there. So for instance, cold air drops like this. So that makes sense, right? So the less temperature you have, the less buoyancy you'll have in your fluid. But you can control these channels individually, which I really like, because the density of these materials are different, of course, because smoke is more dense than air, and the fuel is likely more dense than air. Excellent. So that's just having loads of control over your buoyancy here. And you can see here we go negative on the heat, make it cold, make it, what's it called? Dry ice. Let's have our collision boundary. We get a really nice falling fluid simulation. So that's if you want to make cold simulations, boiling broths and weird stuff like that. Witch's brew. You set those to default. Now, in the buoyancy settings also, we have the control for vorticity, which we've seen in a few things now. We've seen it in PVD, I believe, and also in the flip domain. Vorticity is just how much the fluid will be curling and vorticing. So in a fluid simulation, if I increase this to 20%, we'll see that it really starts to curl up, and you get sort of multiple curls inside curls, and eventually you'll actually end up with problems because you'll be adding more energy than is in the original simulation, and it'll start to expand rapidly. So just watch out for this. You can see here, this actually kind of changes how the scale looks as well. The most sort of vorticing simulations or fluids in real life, they tend to be very high energy, loads of heat and cold differential, or delta, I should probably call that. And they tend to sort of, be very aggressively, and maybe a lot of fuel and a lot of energy coming into the simulation, and they tend to be more energetic at higher scales. But you can increase the vorticity. You can increase the vorticity radius, but just be warned that they can get a bit out of hand if you go too high. But you can see here, you can see how it's vorticing and really churning up, if you like. It's like a turbulence, but it's simulated physically. Okay. This is all about tweaking the look of your simulation, and like I said, I should actually just show the resolution thing as well. So obviously our resolution was quite low there, but if we increase it, I could go to grid maybe. Go to grid, go to 100%. And this is, let's go back to slices again. Yeah. So you can see here, this is a certain level of vorticing, and you can increase the resolution of your sim as well to really exaggerate things. It's going to be very slow if I go for that now. So I've just increased the resolution of our simulation. That will allow more of those detailed vortices to appear. And if I actually reduce the size back down, you tweak this forever. It's very fun to play with ExplosiaFX. There we go. You can see much more detail in the vorticing. And it's not really turbulence. Even though technically it could be turbulence, this is more about how the overall fluid sort of rolls over itself and how it cools down and how they move around each other. You can see actually we've got quite a nice cloud effect there. So you might want to create a cloud. You could use that, cache one frame and render that only. Or you can have it slowly evolving if you reduce the sim speed. Okay, that's vorticity. Pressure and force, we don't need to look at that too much, but essentially what this pressure, max pressure iterations is, essentially what it's saying is that if there's a high pressure change, so say you've got this torus, we actually have a parameter in here called pressure. We're going to look at all the source tag stuff later. But say you've got a pressure and it suddenly changes from a low value to a really high value, sometimes the simulation can't keep up with it and you end up with some erroneous results. Well, this max pressure iterations just means that when the pressure changes, it's going to force a bunch of subframes and it should solve the simulation more accurately, but not too much to worry about. Pressure is important, but I'd say more important on the source side of things, which we'll talk about later. Okay, so that's our buoyancy and our pressure done. Let's look at smoke diffusion. Right, okay, so smoke diffusion, this is talking about how essentially how the fluid moves around itself or moves through the container. So it'll diffuse through the container. And you tend to get diffusion where the densities are very similar. And if I increase, say, for instance, the smoke diffusion, actually, let's do it with heat. The display in heat is kind of cool. Temperature, here we go. So we've got our vorticing. Let's drop our resolution down. We don't need it that high for this demonstration. Heat diffusion, let's put it at 100. Now, what's going to happen here is we're going to end up losing almost all our detail because as the fluid's moving through the simulation, it's not having this extreme difference in sort of densities. So you end up having the heat slowly diffuse through to the next ones instead of jumping across or moving across faster. And this is useful for things like, say you're trying to create a candle, they tend to diffuse quite highly, and it actually can kind of give you the scale look. Let me drop the heat diffusion right back down again, just so we can see a difference. You can see we're getting these detailed curls, and to be honest, I've got the detail a bit low. That's probably not the best example. Let's stop moving our object around. Let's do this properly, shall we? So let's go for a resolution of 4. Make sure we've got some decent vorticity. And let's press play. This is just default. There we go. Just the usual stuff going on. Now, you can see we've got this. It's more about the detail across the fluid. So you can see here we've got this. The boundary is quite a sharp boundary. So actually, where the smoke goes to air, if you like to think of it as air, where the smoke goes to air, we've got this pretty solid boundary. Even though it's not solid, of course, it's over a few voxels, it smooths out. Well, the diffusion will actually smooth that over way more voxels. So if I go to the smoke diffusion now, if I do heat diffusion as well, so it's both, and I press play, you can see that the boundary, the grading is much, much smoother. There we go. So we're actually reducing the amount of detail in our simulation. And like I said, why would you want to do that? Well, candles and things like that tend to have that look where they're much smoother and less sharp in their boundaries. Okay, so that's diffusion, and we've got that in all the other channels as well. We've got it with fuel and heat and smoke and things like that. And it's all about the combination of these parameters, because you might want to just have fuel diffusion, but then everything else diffuses normally. And then that kind of, maybe it's an aerosol spray where it would diffuse quite a lot. That would be an equivalent of a high diffusion fuel. Okay, so in this diffusion parameter, we also have something called viscosity. Now that sounds weird, because when you think of viscosity, you think of liquids, but fluids and liquids are the same things. They are just in different densities. And they have different physical properties, of course, but they can be solved in the same way, the same velocities. All the calculations behind this stuff is going right back to those Navier-Stokes equations that we talked about, but we don't need to worry about that. So what is viscosity in terms of a fluid like this? Well, essentially it's how fast it's going to move around and vortice around itself. So it's the higher the viscosity. Let's go for a really high viscosity, actually. First up, let's put the tag back on. Press play on the default. Let's reduce that down. So why would you want a viscosity in a fluid like this? Well, imagine you're doing ink. Now, ink in a liquid, ink in water, for instance, has a specific look where it's more dense than the water, so it is going to sink. But as it diffuses, as it dissipates, literally as it diffuses, it becomes less dense. And you end up with a kind of balance where some of the ink will actually float upwards and some of the ink will sink down. Well, the viscosity, the higher the viscosity, the more it's going to behave quite like ink. You can get very good ink looks without viscosity, but this is just... Can you see here how it's sort of keeping things... It's diffuse. And if we animated this down, if I just suddenly went to 0, we'd actually return to some more detail into the simulation. Okay, definitely worth playing with all these. They're kind of fun. Now, dissipation, similar to diffusion, but the difference here is it's how it passes it to the next sort of, or how it decays as well as diffuses through the simulation. So when I say decay, I mean it dissipates to 0, so it turns to 0. I mean, I've got it way too high there. Let's reduce it down. Always best to demo these. Okay, so let's press play. Now we can see, we can actually see the fire, the fuel going on in there, the burning fuel. But then the smoke's occurring, and then it's dissipating almost immediately. So it's like it's very low density. It eventually goes invisible. In reality, the molecules of the smoke are actually spreading out so much that they become invisible to the naked eye. That's how I think of it in here anyway. I like to think of it in physical properties, because then it just makes way more sense when you're tweaking stuff. So I've got it really high there. You can go back to 1. So that basically means that it's going to dissipate at this value, or dissipate at this rate even. And you can see here, this is how we can kind of get smoke decaying away. It's probably a little bit artificial, to be honest, because smoke tends to hang around a little bit longer than that, depending on, of course, how dense it is. Heat dissipation. Now, if I go back to our display, in fact, we don't even need to go to our display. We're just going to turn off the smoke channel. So we're just solving heat and temperature. So there we go. And I might not track the heat actually, so that we've got a nice tight domain. There we go. So we're just getting the fuel. And I'm going to pump the amount of fuel that we're pumping into the simulation. So let's go to 300% on our source tag. And you can see there it's throwing the fuel into the simulation. Now, if I whack our dissipation up for our fuel channel, you can see here, obviously that's going way too quickly. There we go, we can reduce it down. And then you tend to get a more natural looking flame when you have a high dissipation value, or sort of at least some dissipation value. You can see it's quite sensitive down at these scales. But yeah, that's how it decays. And if I have none at all, it'll just carry on, and it'll carry on emitting fuel into the scene and simulating. You can see it gets much higher up. It's following the temperature there. Now, a combination of the two, so we could say combining the fuel diffusion, let's go for a fairly high diffusion, and a bit of fuel dissipation, not too much. We can actually get something akin to a candle flame. So that's not enough diffusion, perhaps. There we go, we're starting to get more candle-like flames. So if you, or even a match is a really good example of this. Let's drop our motion off our object again, press play. And here you go, you can see this is much more akin to sort of a single source flame, small scale. And we get that nice flickering at the top there. And the diffusion or the dissipation even might be too high, so if we wanted it to last a bit longer, we just reduce the dissipation down. Or even decrease the burning rate. That would probably be the one way to do it. We'll get onto that in a second. But yeah, we've got all the usual stuff as well. So it's for each of these channels, we also have this fuel ambient and velocity dampening. And what these are, so the fuel ambient essentially is a minimum value for where the fuel will actually begin to dissipate. And that just means that if the fuel isn't below a certain value, it just won't dissipate. So we've got the rate here. You won't be able, it's not always immediately obvious, but essentially what it's saying is it'll keep the fuel, it won't start the dissipation of the fuel below 3 units. So essentially it'll just keep the flame alive for longer. So if you're finding the fuel's burning too quickly, this is one way of kind of keeping it visible in the viewport, in the simulation. Don't tend to use that one too much, to be honest. Velocity dampening. Now this is a way to reduce the dissipation of the fluid across the voxels. And the consequence of that is it stops them from moving from one voxel to the next, or slows their movement from one voxel to the next. So it's kind of like a slow motion thing, but actually it's more of a kind of, it's to do with the dissipation, the movement from one voxel to the next. So we're not getting a scaled down simulation, we're not getting a slowed down simulation, we're getting a purely dampened velocity so that the heat and everything, all the channels don't move as fast to the next voxel. Okay, so many controls, you might not need to use half of them and still get a fantastic result. I'm just going through them because I think it's useful to see what they do and how they apply to the real world stuff, and might be interesting to some of you guys. Okay, so I'm going to drop our diffusion to default, dissipation. Now we can take a look at the burning model. Now, obviously the burning model, we're looking at how the fuel that we've put into the simulation, this is how clever this is. I love, this is why ExplosiaFX is so fantastic. And you can think of it physically. So we have chemical burning models, we have a simple burning model and a custom burning model. But the basics are, you're emitting fuel into the simulation. You then have an ignition point for that fuel. So it's an ignition heat. So in real life, you give enough heat energy to a fuel, it will ignite and you get a combustion, you get ignition. And then that starts to generate carbon or smoke. Converts the fuel, carbon fuel, into a smoke. And this is all done for you, of course, behind the scenes, but you do have control over the rates at which this occurs, the rates at which this heat is generated or is igniting as well. So let's take a look at that now, and we'll work with some animated parameters and test out the different models. And we'll start with the chemical burning model, which is the default, and also because the other two, simple and custom are kind of spin-offs of chemical, or a simplification, of course, for simple. But it's also useful to describe this as a chemical process. So in the real world, let me press play actually on our solver. In fact, I'm going to reset our explosion container, just make sure everything's back to default. Maybe increase the voxel size a bit just to get nice quick playback. We'll just let this loop around. So in the real world, you have a few things that you need for burning or combustion. And you need a fuel, you need an oxidizer, which is usually oxygen, although not always oxygen, and you need heat. Now the heat is to get the reaction going between the oxidizer and the fuel, so you need energy input, and that comes in the form of usually quite a high heat, and the fuel will then combust, start to burn and consume the fuel, and then produce a gas. Now, it's usually a gas and particulates. It's essentially, so imagine burning a high carbon fuel like petrol or gasoline. You'll produce a really black carbon smoke. And then other things like wood, solid smokes, they tend to be a bit more white, producing different colors smokes. And that's kind of a side note, but worth thinking about when you're creating smoke coming off items or generating off fuel. So how does that relate to our explosion container? Well, of course, we have a smoke, fuel, and a heat channel. There's no oxidizer here, but you can kind of think of the fuel as an oxidizing reaction. It's the important part of that reaction. We don't need to see the oxidizer because that essentially is air, unless you're inputting it like a rocket fuel. So let's have a look at go back to our simulation tab and look at our burning rate. Now, if I increase our ignition heat to 1, you'll see something happening as it loops back round. You'll see we are no longer burning the fuel. The fuel is falling. Even though, by the way, even though the display is like this orange color, we can look at our temperature here. And you can see it's quite cold. So nothing's burning at the moment because it's not reaching the ignition temperature. And the reason there's not much temperature is that it's at 100% heat, and it's the ignition temperature for this is 1. So basically that's 100%. So if we drop that down to 0.5, for instance, let's see if it actually catches at 0.5. Not quite. 0.2. There we go. So what we could do is we could actually animate this up. So we could actually say ignition heat of 0. Let's just create some keyframes. Oops, 1. We don't need to worry about this one too much. This is called burning rate variation. This is just between each voxel, the rate of the burning will occur at different rates depending on the slider. Now that's not too important, but it generally gives a little bit of a more natural sort of burn through a fuel system than it would if you just have it with none at all. Worth keeping on. So we're going to start at 0 ignition heat, and then we're going to go... Oh, sorry, I should be the vice versa. Let me put a keyframe down for 1. And let me right-click this. By the way, if you shift-select your keyframes in this in the timeline here, right-click it, go to Edit, you can quickly reverse that sequence. It's quite useful. I use that one a lot. I'll turn off my container. Let's slide them to frame 15. Turn our container back on. Go back to the beginning. Now, we're not going to be igniting. We're not going to be turning... Or actually, make it much further down the timeline. There we go. Press play. And we can see here our fuel comes out, and you can see it's sinking, so there's not enough heat. And then eventually, when I lower the ignition temperature, it suddenly ignites and starts producing heat. So one thing to know about a combustion or burning reaction is that if there's enough fuel and enough oxidizer, the fuel will generate heat. The reaction between those things will generate more heat. So you've got an ignition heat, and then you get more heat from the reaction itself. And that becomes a self-sustaining thing if there's enough fuel and oxidizer around, which is why you get a burning flame for a while as it uses up the fuel and whilst it consumes the oxygen in the system. So in this scenario, I'm actually faking it a little bit. I'm actually reducing the ignition heat, whereas in reality, we really should be increasing the ignition element or something that's going to ignite the stuff. So this is just the fuel. And then at this point, it becomes burning fuel and it starts to produce smoke. That's the basics of a burning model. Let me go to ignition heat of 0. The max heat is how much heat will be generated by the, essentially will be generated by this reaction. So we can increase the heat and it'll actually make it more buoyant and move faster. And of course we can animate all the other parameters down as well. So that's the chemical one. Now there are some issues with the chemical one, like the ignition heat is quite sensitive. So if I set it to 0.5 for instance, let's see if that actually ignites. No. Then we go to our source, and then we can actually animate this heat up. Oh, actually, no, let's not animate. Let's do something else. Let's do something interesting. Let's use another object. So I'm adding a sphere to our scene. I'm going to drag the lazy way of doing it is I just control dragged the tag onto this object. And I'm going to drop all the other channels out of this. I don't need any pressure, any fuel. I just want this to be our igniter. So let's take the heat out of this one as well. So if I turn off the original torus and I press play now, it's going to track heat from this one. And if I go to our display tab, we can go to our temperature and you'll see that's producing temperature. But it's not visible because obviously we don't need to render that channel. We're just going to bring it over. Let's put our torus back on. So if I press play through this simulation, you can see the adaptive bounds, by the way, is following this temperature here and the temperature there. Now, this one here is the fuel is sinking to the ground. If I bring this in here, as long as the temperature value is hitting the threshold, I can actually ignite the fluid. Can you see that? It's actually caught fire. And eventually it'll actually catch all of that. I should increase the timeline. Of course, more frames, better. Let's demonstrate that again. I should get rid of the grid, by the way. We don't need to see that. Show bounds, get rid of that. So you can see at the moment it's sinking, it's falling through the bottom of the container. I bring in our ignition source. And there we go. It starts to turn it back into smoke and starts to burn. Some fuel still escaping. So if I bring our thing through there, just catch it all alight. And then eventually it all catches alight and we get this cool exothermic reaction. So that's how we can ignite things. We can burn things. We can also do it just on the one tag. So let's press play. We can actually increase the heat until it hits the threshold of where it would ignite. So let's go for 500. And there we go. And we can, of course, animate that one up as well. So we can go from 0 to 60. We might take a little bit a deeper look at this in the sources section. So is it going to make it? There we go. There's the moment of ignition. Is that? So it's as if you were heating it up, and then all of a sudden it combusts, and then we end up with this nice smoke being produced as well. So that's awesome. What else can we look at in the burning model? Let's put our heat back to 100%. Solver. Oops, simulation even. Let's reset our ignition heat to just straight away. I've shown you the max heat. The max heat is just how much heat is generated by the reaction. To be honest, that one is more important when it comes to the custom one, but we'll show you that in a minute. Let's go to simple. Simple is very similar to the chemical reaction. However, this time it's much more, it's a linear diffusion of the fuel. So actually we can see it's actually getting ignited and burnt away much, much quicker. Let's double check that we've got enough heat. Yeah. So if I increase the ignition temperature, we can kind of get a much more predictable reaction with our heat. Whereas the burning model uses sort of more realistic sort of equations and stuff to model actual fuel burning. Whereas this one is much simpler. Like you can get probably more predictable results out of the simple one. But I think I like using the chemical one because it just looks more natural when you get into it. So let's go to custom. Now this is where it gets really interesting. So in custom, you have control of every single channel. We have control of separate heat production, smoke from the heat, smoke from fuel, gas expansion. This one's an important one if you're doing explosions. Burn rate variation, ignition heat and max heat we've already been dealing with. So if I actually drop our ignition heat, make sure everything just ignites straight from the off. And you can see that looks pretty similar to the chemical and the simple modes. Tell you what, should we give some motion to this? That always looks good with motion. There we go. We can see the fire coming in, the flame coming in, and burning and going up, just like we've had before. Now, if I take our burning, for instance, and I make that 0, essentially we'll have no chance of it turning into another gas, into the smoke. So the fuel remains fuel and it doesn't burn. But we can animate that up, and then it becomes the burning rate is increased. So this is a burning rate. So as we increase it, obviously the fuel burns quicker. And we can also use curves for this. So this spline here, so once the fuel's emitted, you can see we can actually keep it as fuel for longer, and then eventually it'll combust. And even there, we're actually getting fuel remaining in the system for quite some time. And that's a multiplier, by the way, against this slider. So definitely fun to play with those. So let's reset that one. Now, heat production. So heat production is when we have, like I said before, your fuel starts to burn and it produces its own heat. And in the chemical reaction one, that's based on real world stuff. This in here is abstract, and you can just slide it around however you like. So for instance, let me actually turn off, I'll make the ignition heat really low. The heat really low. And let's make our ignition temperature. Let's see if this catches fire here. So it just about catches fire there, but there's not much heat production going on right now. So if I actually turn the heat production to 0, we should see the simulation sync because there's no heat being generated. And if I go to our display, change it to temperature, you can see we're right at the 0 point of the temperature, and it's sinking through the ground. However, if I go back to our simulation tab and our heat production to 1 starts to increase and our buoyancy returns to normal, and we actually get a rising smoke, rising fluid. And if I increase the heat production to a 10, it won't immediately jump to that because we're limiting it down here. So this is where this max heat parameter comes in. Let's go to 10 on that. And you can start to see it gets very hot very quickly and rises much quicker as well. So this is just a way of having much finer control over each of your channels and how it produces the gas and stuff. Now if I gas expansion, let's do a bit of a higher. Let's make the max heat 1 and 1. Oh, we do need more heat. There we go. Display. Let's go to fuel and smoke. Now the gas expansion should be expanding the system, but it's actually not doing that too much. This is definitely worth playing around with though. The burning rate variation, like I said, is just the variation between each of the voxels. And you're getting a pretty natural looking simulation here. You could increase the heat, maybe have more heat, more burning. See the fuel there. So if you've got a lot of fuel coming into your simulation, you might want the burning rate to be much higher. So this is where we'd go into here and we'd crank the fuel production up massively. So you can see there, loads of fuel. In fact, we're producing so much fuel, it's actually weighing down the simulation. So we could say, go back into the simulation here and make sure that we're producing. We could either increase the buoyancy of the fluid, or we can increase the heat production, perhaps. We're getting into some crazy, unrealistic fluids right now, but interesting nonetheless. Let's go back to our buoyancy tab. Let's make the fuel just 0 buoyancy. There we go. We're getting very, very dense smoke. You can see that's quite thick there. Yeah. Cool. So yeah, that's the burning models. Worth playing around with them to see what suits your needs. I would say mostly I'm using the chemical one, but you might find a scenario where you need to be using perhaps the custom model. Okay. All right. Next up, we're going to take a look at the forces tab. Now, this is just a sort of on the end of this part of the look at the solver simulation and things. We're just this is like an inbuilt modifier for you, so you don't have to add any modifiers to your scene, but you can have a wind object or a turbulence in the system. I think I need to reset my solver. Go to solver, reset to defaults. There we go, back to normal-ish. Oh, we're still producing loads of fuel, that's why. 300, 100, that's back to default. Okay, so let's have a look at those two options in here, the forces. Let's first have a look at turbulence, because that doesn't require an extra object. And the reason this is in here and we'll talk about this in the sources and modifiers section, is that the modifiers from XP work with the Explosia domain, which is fantastic. However, there is a bit of an issue with some of the turbulence modes that they diffuse the simulation too much and too quickly. So the guys added this inbuilt version of turbulence, and you can see here we get this really nice curling turbulence, sort of as if it's in like a very aggressive system. Might change the scale of the sim as well. And you can change these to max and add modes. You see that it's actually diffusing the simulation quite a bit. And then there's a wind one. So if I press pause, go back here. Let's create a wind object. Now this wind object is a unique object. It's just for ExplosiaFX. And it's the same thing. It avoids collapsing the fluid too much or diffusing the fluid too much. But you can see we get some nice control over this. If I rotate it round, we get wind going back the other way. And I really enjoy having that amount of control over the fluid. Where it gets really cool, though, is when you use it with the XP modifiers. And we'll look at that in the next section where we're going to take a look at the sources, the modifiers, and the advection stuff, which is also fantastic. All right, I'll see you in the next video.